lilKernel is the project. I first want to quickly tell how I came up to that. So I worked this year on frequently asked questions for support project, and the main idea of it was detect frequently asked questions, but on unlabeled data, because most of solutions which were already available were for labeled data. So some support agent should have already tells that this ticket is related to this frequently asked question, and it's not actually a good solution because you need a lot of labor for doing such stuff, and that's why I was going towards like unsupervised solution, and it's actually like proofs of this, not proofs, but like why it would be good. It would be beneficial for product designers, like to evaluate shortcomings and to identify weaknesses in our product. But yeah, actually, it is not my project for the hackathon, but it was the reason why I thought about efficiency of actually summarizing support tickets, because algorithm I came with is quite cheaper in terms of computations. You just get summaries and tickets embeddings, and then you calculate similarity scores between each two available tickets, and you then take some threshold similarity score like 0.8, and you calculate how many tickets have a similarity score greater than that. And this way, it's kind of form of clustering, and the tickets with the highest frequency are the tickets that are frequently asked, and it actually works quite well. But what I used, like the bottleneck of this solution, it's actually get summaries of the tickets, and what I used first for that, it was OpenAI compilations create, and I used it on CPU. So I just had the most simple and the most not efficient solution that could be, and for this reason, 300 tickets was summarizing like for a long time, and I only could perform this method like month by month, because you have not so many tickets in 1 month. But what is really interesting is to try to perform it like on big data, so we can see like which questions persists frequently asked through the time. So I thought that I need to work on efficiency of this summarizing thing, and it was time when kernels came into my life. Like I just heard from my friends about that, and actually, I think it's something we all should consider for our product in some way, because actually kernels is something which is behind um, NVIDIA and NVIDIA success, like because kernels can be performed only on NVIDIA's GPUs, and that's why it's a bit challenging with Apple Silicon to do that, because yeah, you can do that locally. You need to use Colab. So for Hackathon, I used Octa Colab, where I had an A100 GPU, I believe, from NVIDIA, and yeah, here I just quickly describe the main idea behind CUDA kernels, and I will not go deep into it because it's not interesting for everyone, but I have a link for my presentation I did on that, and if anyone interested, you can take a look. But the idea I wanted to highlight anyway is like it's the architecture of our GPU, and to understand why the main idea of kernels are using threads and using blocks, and this way you kind of it's intuitively a bit similar to chunking, but where it comes from GPU architecture. So we have a lot of cores on GPU, and we kind of divide in the calculations this way, that we will run like one operation on one GPU like same time. I think I framed it not good. Like you run operations in parallel, like every core will be in execution, and that's why it's efficient. And it's like the example for vector addition. And yeah, it's quite a good example because it's easy to understand, but what is used here is C, and like it's you should think about it this way: like we have PyTorch as the highest level framework, and we have lilKernel as the lowest level framework, and in between we have Triton, and it's something a lot of people use. Like in Triton, you can already see this threads blocks thing, but you shouldn't go so deep like into C. And actually, my first idea for the hackathon was to proceed with lilKernel, but it's a bit hard to make it to compile it like in Colab and stuff. And as I have Apple Silicon computer, I cannot do it locally. So yeah, I proceed with Triton. And so we're going ahead and driving GPU usage to have efficiency gain. And yeah, what I discussed just now, like should you use pure CUDA or Triton? And why would you need it? Like it could be sounds like, you know, fun idea, like maybe for education, to write lilKernel, like for transformer, like to understand how everything works. But what we need, like for our customers, is like efficiency. So you need to like what is more efficient is to think about the bottlenecks of the transformer architecture and apply Triton kernels where this actual bottlenecks are located. And for summarization, um, it's important to know also that you have extractive and abstractive summarization. And extractive summarization, it's when you just highlight the most important sentences in a text, but nobody cares about that these days because we have LLMs and they can do abstractive summarization. Why they can do it? Because they have encoder and decoder. And actually, in encoder-decoder mechanism, it's the main bottleneck. It's softmax, matrix multiplication, normalization functions. And if they are not parallelized efficiently, it's not a good, they can perform like slowness in performance. Sorry for my English. And yeah, so I came with my solution. It's I used as a model and tokenizer utilized BART, and like where I applied kernel, actually, like I applied custom Triton kernel for softmax operation, and this kernel efficiently handles like row-wise computation with numerical stability and parallel normalization for GPU acceleration. And also what I did is like custom Triton attention layer is maybe looks like not super good a solution because it's not multi-head attention, but actually the result was quite good. I was even surprised. And yeah, I used PyTorch for profiling. And yeah, actually, what I comparing here is the summarization pipeline written in pure PyTorch and pipeline using written using like this Triton kernel. And yeah, I'm sorry if in this slide is a bit not big, but yeah, I actually asked the GPT to analyze like profiles from the profiler, and the second solution is better, like for sure. It performs profile one across all critical operations, and it performs fast execution times for matrix multiplication attention. And actually, it's a very fun thing to like go deep into if you are interested. Is you know, when you're going, you can see these little operations, and it's coming from C++ syntaxes, like this art and linear stuff, and you can see how much time it executes on CPU and how much time it executes on GPU. So. And yeah, it's just if you consider like trying solutions, comparing your Triton solution, like your CUDA solution, or comparing with just pure PyTorch, you can use it and like know a lot of new stuff. And yeah, if only one kernel gave an improvement, what else could be done? Actually, like what I tried also do, but like didn't manage because of time, and it's quite complex. It's optimize beam search for Triton, and develop like Triton kernels for parallelized beam search scoring. And what is important, like that actually it's the main bottleneck of transformer architecture. It is in decoder, it's not in encoder, but yeah, but
Alina,
even
time check, just 1 minute, okay?
Yeah, thank you. And yeah, and you can also introduce flash attention instead of multi-head attention. We all heard about attention, but yeah. Maybe it's special for my model, like flash attention is already introduced in some models on Hugging Face. You just can go straight into it. So yeah, I managed to summarize 4,000 tickets in 1 hour and 2 minutes. And as I said before, like with OpenAI compilation and CPU, like, and it's not fair to compare because using API on a CPU and like using like more low-level solution on really powerful GPU is not comparable. But yeah, that's why I compared. I had like as a baseline PyTorch solution. And yeah, what I did, and I just wanted to show you very quick. Yeah, it's this fused attention. It's like flash attention on Triton. It's like this code looks like it looks fine. The only thing is this blocks and threads things, and you can see them here, but you cannot go like deep down into C++. And it's actually my notebook in Octo environment, and yeah, it was. Yeah, it's actually the one where I introduced Triton, so nothing too stressing, but yeah, you need to just time to make it work. And like you first need to like quantize I don't know, like what you have. Like the best approach is like you have your PyTorch solution. If it's not bad, you go to Triton, and you think if it will gain your efficiency, because of course there are a lot of people who are already working on this efficiency, like on make PyTorch efficient. And if you see that your Triton solution is not good enough, you can go deeper into CUDA. So yeah, it was like pretty much what I prepared for today.
Great, thank you, Alina.